for the opportunity, and good evening, everybody. Thank you for being here, and the Toastmasters and the new folks that I'll be meeting today. So the topic for the talk that I have today is called AI for everyone. And I want to clarify what I mean by that, because I know there are people that don't want to use AI. So I'm not saying everybody should use it. What I'm saying is the AI that you're building should be unbiased, inclusive, and it should be reaching everybody that wants to use it. So we want to make sure that AI literacy is for everybody, accessible. And that's my goal for the talk today, to share that knowledge. A little bit about myself. I also have my degree, electrical engineering degree from Wayne State University, and that's when I joined IEEE 10 years ago. I was more active back then, just getting more active in IEEE now. After graduating, I have been working in the automotive industry at GM, mostly in the ADAS domain, designing and validating the features such as automatic emergency braking, forward collision alert, intersection collision mitigation, that kind of stuff. For my PhD, which I'm also getting from Wayne State University, I'm using AI and machine learning to solve problems for the real world. So our goal is to have a personal robot for people, for elderly people who are living alone, so that this robot can help them do chores or find events when, let's say, they have a fall detection, then you're able to get assistance in time. Through the course of my PhD, the machine learning applications that I worked, they span both computer vision, but more specifically, I would say audio machine learning. That's where my expertise is in right now. And that includes speech processing and speech translation as well. I believe that future is where AI and humans are working together. You know that the cat is already out of the bag, AI. It's not going back, so we have to learn to live with it and use it for our benefits. So lots of uses of AI, but there are also potential concerns, as we all know, because it's a new field. It needs to be carefully thought about, regulated. So all of those things are not fully there yet. So there's some concerns. And right now, everybody plays a critical role in making sure that we're building AI that we actually want to have, that is actually going to be beneficial for the world in general. So let's start with a question. How many of you use AI in your daily life in any form? Show it there. Okay. I was hoping everybody would raise their hands, and everybody did.
I think the real answer is we're being used by AI every day. They're reading our email.
Yes.
And all sorts of stuff that we don't even know about.
Absolutely. So let's look at some of the interactions that we do with AI on our daily basis, whether we know or not. Some of the examples here. Let's say we go to a trip to a country where they speak language different than ours. We use Google Translator to do the translations. Or when you're drafting an email, it gives us suggestions of how to form a sentence in a succinct manner, or spelling corrections. Those are applications of AI. And then also conversational AI is like Siri, Alexa, where we can give them speech command and they give us a response. These are all applications of AI, and more specifically, these are applications of natural language processing, which is a subfield of AI. The outline for the talk today is I will be introducing various subfields in AI, how we train the models, how we evaluate them, And then that will be the most of the focus. And then we'll also discuss the benefits of AI, the applications, the problems that it should be solving, it is solving, and also what are the risks out there with the AI that we have. Let's start with the basic question. What is artificial intelligence?
It's the application of neural networks.
Yes, yes.
Or you're interacting with something and you don't know whether it's real or artificial.
Yes.
You can't tell the difference.
Sure. So we don't have a clear definition of what artificial intelligence is. This was a concept, and the term itself was coined in 1956. It was a concept where we want to achieve human level intelligence. That's where artificial intelligence term came from. It's a concept. So as it is used today, it's a bit of an ambiguous term. It's used as a catch-all for anytime we see a machine that is smart enough to be able to have a conversation or make decisions. So I would say it's a little bit of an ambiguous term. We don't have like a set definition for artificial intelligence. In fact, this is actually a big umbrella that has many, many subdomains inside. The big one is machine learning. So here, machine learning is actually an approach to get to artificial intelligence. And there are several ways to do that, and what that we call those models, and we'll review some of them today. Within machine learning, we have a deep learning. That's where neural networks are. That's what neural networks is, deep learning. Deep learning has been around for a long time, but it became popular in the early 2000s. You probably have heard of the name Jack Hinton. He's like the godfather of deep learning. His research popularized deep learning in the early 2000s. And since then, deep learning is what most people think is AI. With deep learning, so machine learning and deep learning are approaches to achieve artificial intelligence. Now, depending upon what type of problems we are solving, there are subdomains. So let's say I want to solve a image or video. I have a data that is image or video, and I want to solve a machine learning problem, like to do a classification. So that sort of stuff is called computer vision. So it is application of machine learning or deep learning to images or videos. That's computer vision. Now, if we are processing textual data, sorry, not just textual data, if we are processing natural language, which is a language that we humans talk or write in, could be speech or text. If we are solving those problems with deep learning, machine learning, that domain is called natural language processing. Then we have recommender systems. We use them pretty much every day. So if you use YouTube or watch Netflix, we know that they know what we want to watch because they give us suggestions. Why? Because they know our history. So they have algorithms behind these new YouTube and Netflix to recommend the videos and the movies that you should watch. So those are recommender systems. Next, we have a popular term, which is popular these days, called generative AI. So generative AI is nothing, but here the AI is able to generate new stuff. It's able to generate new text, new images, new audio from the data that it was trained on. Where do you think that ChatGPT falls under? Where do you think it falls?
The green one.
The green one, yes. Okay, is it on the left side or the right side?
It uses all sides.
Well,
On the right side?
Right side.
Yes.
Is right side.
Yes. So ChatGPT belongs to a family of models called large language models. And they're generative AI because they generate text, and also we are solving a natural language processing problem. So it's somewhere there. Now, what about if I want to solve a more complex problem where I want to teach a robot, I want to give the command to a robot either speech command or a text command, and I want it to be able to solve a visual task. So we are solving two problems. I apologize, I don't know why the video is slow. It wasn't as slow as it is showing here. So we are solving natural language processing problem and computer vision problem at the same time. How do we do that? We actually have a technique called multi-model learning. So here, just like as humans, when we are trying to solve a problem or perceive the world around us, we don't use just one sense. We use more than one sense most of the time to interact with the world. So here, same thing, we can train the model to learn multimodalities at the same time. So that means the chart that the Venn diagram that I showed on the previous slide, the lines are not always as distinct. They become blurry when we want to solve a more complex problem, like a multi-model problem. By the way, this paper RP2, this came out just last week from Google. If you want to learn more how they did this is a paper I would suggest reading. Okay, so that was the basics, just the terminology out there, different areas, different subfields in the AI. Now let's dive deeper into what actually is AI. So I want to start off with a basic term called model, because when we talk about machine learning or deep learning, even the large language model, there's a word model, but what actually is that? So we'll spend some time just understanding what model actually means. Let's start with a very simple example. And again, I apologize because everybody here is an engineer or a professor. You already know this answer, but let's just give it a try. So if I give you a sequence of numbers, and what would be the next number here?
64.
64. How do you get to that conclusion?
I was thinking of the Beatles song.
How did we get to this answer?
We detected
Each
a
number is
pattern.
added by
Yes.
itself.
Yes. So our brain, we saw there was a pattern, and that pattern helped us determine what the next number was going to be. So that's what machine learning and deep learning does. It learns from the data. It learns what is the pattern in the data, and it's able to be used then later on a data that it has never used before. The difference is that this problem is simple because we have learned the math. But in real life, the data is not as simple. But in real life, the data is high dimensional. So that's where we need deep learning or machine learning to learn from the data. So if I was to describe this data set, how would I describe this? If I have to give the recipe to a neighbor, if you know this recipe, then you will be able to predict numbers in this sequence. What is that recipe?
Tell them
2 to the
which
power.
number is double, just take patterns.
Exactly.
That's a mathematical model.
Exactly. So it's basically 2 to the x, right? If you know that, and if I give you any value of x, we know what the next number is going to be, or any number is going to be. So that's a recipe for this problem. I wouldn't call it a model. I mean, it is a model, but we don't call it that way because this is a very basic problem. But now we're thinking in terms of what model means to a machine learning. Let's take a more complex problem. Let's say we have a data, and we have a historic data for an individual, and that data tells me the calorie intake for that person and how their weight fluctuates with the calorie intake, and this is my data. And I want to find a trend in this data. What is a trend in this data, or pattern in this data?
Increased calories increases weight.
Yes. Yes. So increase calories, increase in weight, but how? Is it a linear relationship, or is it exponential, or is it more wiggly, which we don't have a standard mathematical function for. So there are several choices of fitting a line or exponential function to existing data. There are several choices. So let's stick with the simpler one, which is the linear model. How do we describe a line? So this is just y equals mx plus b. We have a output, y is weight, and calories intake is the x, and then you have slope and then intercept, right? So this is how we describe that data by equation for line, because that data sort of fits the line. So if I know what my equation for line is, I can easily tell the weight of the person if I know the calorie intake. Now I'm going to change the variables a little bit. The same equation, but I just changed the variable m to w1 and the variable b to w0. Why do I do that? Because machine learning, they invented new terminology. So to introduce the new terminology, I just changed the variables. Same equation. Okay. So now we have a machine learning model called linear regression model. And in machine learning speaks, W's are called weight and X is called a feature. So here, when we say we want to train a machine learning model, what we want is, we want it to learn from the data what is the value of W1 and the bias. So, you have just been introduced to the very basic machine learning model. It's called a linear regression model.
So next time some professor throws these terms around, you know what they mean.
Exactly. So this was not as bad because we know, we have learned in high school how to find the equation of a line. If we are given two values on the y-axis and two values on the x-axis, we know how to find the intercept, we know how to find the bias, the slope I mean, or in other words, we know how to find the weight, we know how to find the bias. So all the equation for a line is simple, we can do that by hand. We don't really need a machine learning or a computer to solve this simple problem when we have just one variable here. Now let's move on to a little bit more complicated problem, sort of a real world problem. Here we're given a historic data, and I am told that these are all the, let's call them features, that's what we call them in machine learning. These are different inputs, the attributes or features that affect the price of a house. So this is the data that we're given. And we want to learn from this data, how can we predict the house price if I'm given all these attributes for some location. So we want to build that prediction model. How would we do that?
We'd have to build a complex model with many weights.
Yes.
And maybe more than one bias.
Absolutely. Absolutely. So here, as a machine learning practitioner, we have a choice. There are several machine learning models. We just learned about the linear regression model. So let's go with that. So let's say we choose to use the linear regression model to fit this data and see if it works. The linear regression model is simply the linear combination of the inputs. Here I chose only 4 inputs out of the several I have there. But that's again a choice a machine learning practitioner would have to make. Which features do I want to use? Do I want to use all of these features? I'm just using 4 for simplicity. So this, again, a linear regression equation, linear combination of all the variables that I'm interested in, x1, x2, x3, x4, which are basically area, bedroom, bathroom, stories. Now this problem I can't solve by hand. I can't find what are all these weights. I can't find that by hand with just this information. So that's where we need the machine to learn. So that's where we train or fit the model to a data. Okay, So how do we actually train a model? So we understand what a model is. Model is nothing but a mathematical formula that takes some input and gives some output. So it's just a model. But how do we train the model? So I only have the data. How do I train a model once I've identified that this is the model I want to use? So that's where applied machine learning comes into play. There are many different ways we can train a model. Just like there are many different ways to teach a child or for us to learn something new, there are a few different ways we can train a model to learn something new. Some of them are supervised, unsupervised. So let's take a look at supervised and unsupervised. So let's say I want to teach a machine to identify that if I give a bunch of pictures, I want the machine to learn which picture contains a dog versus which picture contains a cat. One way to do that is I give it the labeled examples. I say, hey, this is what a dog looks like and this is what a cat looks like, and I label those images. And I give this labeled data to the machine learning and I let it learn from those labeled data. That is called supervised learning. But let's say I don't have the labels. Let's say it's more tedious to add the labels, because for machine learning, we do need more examples. So labeling each image is a tedious task. So let's say I don't have the labels. Then how do we train the model? So in those cases, we just give it the data and we say, hey, learn from the data. Figure it out. So that is unsupervised learning. And then you have semi-supervised or self-supervised, a little bit more complex, but supervised and unsupervised are the two extremes of how you train models. And then we have reinforcement learning, and he can tell you more because his PhD is in reinforcement learning. But here, basically what we do in reinforcement learning is you give a task, and then if the model gives you a result that you want, then you reward it, and it gets better at it. If it does not do well at a task, you penalize it, and so it's feedback. So we do this with a lot of examples over a lot of iterations. Then eventually we want to make sure that it works, right? And the goal is that we want the model to work on a new data that it has never seen before. So how do we do that? So that's where evaluation plays a critical role. So when we are training the model with all these examples, we define a metric. We define a metric and we say, if this metric is mapped, like accuracy as an example, or root mean square as an example, then this is good enough. So then once we meet that evaluation criteria, the final test of the model is when we give it a data that it has never seen before. And then we try to find the metric on that new set of data. And that's the real evaluation for the model. That's if it does well on the training data but does not do well on the test data, then we call it overfitting. So it has learned its data so well, but it has memorized all of that. It has not learned anything, it's just memorized. So that's called overfitting. On the other extreme, we have underfitting. So if it learns from the data, but it's not performing well on its own training data, that's underfitting. We know that model is not good. But overfitting is a problem because sometimes it gives us an illusion that it's good, but it's only good for that data set that it saw in the training. So overfitting is, both are not good, but overfitting is really bad because that can pass through our judgment. Just like linear regression, there are a bunch of other machine learning models out there, and here are names of some of them. We won't go into the details. Just want to share that there is a whole box of models that we can try to fit our data. And this is where applied machine learning comes into play. So you want to try, you want to start with an intelligent guess that comes from practice, and then you want to try different models and see which one works for the data that we have or the problem that we're trying to solve. So that was all about machine learning. Let's do a brain teaser. Find a cat.
It's
It's right there.
They're all cats, lots of cats.
There's one with the closed eyes.
Oh.
And is that because all the others are open, so they must be owls, so it's probably nighttime?
Sure, you can think of it that way. But if given enough time, we can figure out that there is some anomaly here. How did we do that? How did we do that?
comparing.
Yes. So again, we looked for some anomaly, we saw there were some patterns. Like you said, all had eyes open and one with no eyes. So we were looking for a pattern, right? How would we teach a machine to identify a cat if I give it an image of a cat? What kind of features would you describe and give to the machine and say, hey, if you see these features, then this is a cat.
The structure of the face, the distance between eyes, shape of eyes, other features that characterize the cat,
Yes,
all sorts of attributes.
Yes. yes. And the list is not small
Yes.
because we have a lot of different types of cats, a lot of different sizes, a lot of different shapes, and they can be in any different background, like in the grass or in the house. So we want the model to identify a cat no matter where that cat is, no matter what that cat looks like. So we want it to be general. How do we do that? So for that, we need to identify as a human, if we want to use the existing machine learning models that we saw previously, as a human, we need to define the features. And those features we feed into the machine learning model and we let it learn from there. So the result is going to be as good as the features that we say are important, right? So this is not a simple problem. So the existing machine learning models that we saw before, they can do the job, but they're not the best at solving harder problems where we have more dimensions in the data. So that's where deep learning comes into play. So let's dive deeper into deep learning. By the way, if you have questions, we can do the questions while we are doing the presentation. Okay, so let's start with the basics again. Deep learning is a subfield again in AI, and within AI, like I said, AI is a idea or concept, but we have approaches. Like machine learning is an approach, deep learning is an approach. So deep learning is also an approach to artificial intelligence where we want to learn from the data. But here the models are more complex than the models that we saw when we learned about machine learning. Here, what we see is the very basic model in deep learning. By the way, deep learning is inspired by human brain. We have neurons. So here we are trying to build an artificial neuron, which we also call perceptron. So this is the basic machine learning model. And it's very simple actually if we go through the individual circles here. So here is just the inputs, x1, x2, x3. Think of it as different features. And then these are just the weights. So for different features, we want to learn how important those features are towards my final output. So that's what the weights are. And then we just do the summation. So here you do x1 times w1, x2 times w2, and then you sum to the summation at the end. And then we have something here called activation function. So activation function is you define a threshold. So if we are solving a classification problem, then you define a activation function. You say that if my end result is higher than some threshold, classify that as 0. If it is lower, then classify. So this is the basic unit of deep learning. One thing I want to point out before we learn about more advanced deep learning models is that deep learning models are compute intensive. They do need GPUs, lot of GPUs to train, because not only because they are complex, they also need lot of data, lot of examples to learn from. However, they make things a little bit easier on human part, that we don't have to define the features upfront. We just give the data to the model with either labels or no labels, depending upon how we are solving the problem, and it is able to figure out over time which features are important in that data. So that's the benefit and just some drawbacks. Let's move on to a more complex machine learning model, deep learning model, which we call multi-layer perceptron. So as the name suggests, it's still a perceptron, but it has more than one layer. Here, again, we have the inputs, but rather than having just one layer, which we had in the previous slide, it has one layer, second layer, third layer. We can add more layers. And then again, we do the summation and the encapsulation. So it's really the same, but what has changed is it has more layers. And we call these hidden layers. That's just the terminology we use in deep learning. And also, the reason why deep learning is called deep is because of these more layers. When we have more than one layer, then we call it deep learning, because we have a deep model. So when we train a model, in this case, when we train the multi-layer perceptron, what it is actually learning from the data is it's learning which of these connections are important, and which of these, and what is the value? What is the value of each of these weights? So that's what it's trying to learn. Okay, let's move on to a even more complicated deep learning model, which we call convolution neural network. Convolution neural network is used to solve problems that are related to images or videos. So it works best on the image data. So what's the difference between convolution neural network and multi-layer perceptron? So the difference is the mathematical operation. So the mathematical operation that we do in the convolution neural network is no longer the simple summation and multiplication. It's more complex. It is convolutions. If you're an electrical engineer, we study convolutions, but the convolution operation in machine learning or deep learning area is not the same definition. It's actually more simple. So let's look at an example of what a convolution looks like. So here, this is an image frame, and these are just the values of the pixel. And then we have to define this, what we call filter or a kernel. So what I'm going to do is, I'm going to take this filter or a kernel, and I'm going to do the convolutions, which is nothing but to take this value, 4 times 0 plus 0 times 0. You're doing the multiplication and adding all of those. You're basically representing this square by one number at the end after you do the convolutions. So I'm going to take this filter, I'm going to slide it across and down until I'm covered the whole image, and that is a convolution operation that we do on an image. So then, we actually don't use just one layer. We actually use a lot of these convolution layers. So for example, here, just a representation. We have a lot of layers. So one layer, and then there are other things such as pooling and stuff. So a lot of details here, but I'm skipping those details. The basic idea is that these are called convolution neural networks because we do convolutions. And again, these are deep neural networks because we use more than one layer to form a network.
Can I ask a question?
Yes,
or I
yes.
can wait?
Absolutely.
So here in the before the neural network, feature selection is very critical, right?
Yes, yes.
In this case, the filter selection would be very critical, right? because you have to know what filter you are choosing.
Yes, absolutely, absolutely. So that's where when somebody tells you AI is smart, it's not. It's the humans that are building the AIs who are doing all these selections, who are coming up with these models, right? But yeah, see, the filter selection is important in this case.
And the values that were given to those pixels, those are like just for an example, or
Just for an example.
0, 1, 2, 2, that's, and it is
Yes.
again decided by human.
No. Pixel value would be whatever the image. So when we have an image, when we load that image into any, like even in MATLAB, it has numerical values each. Yeah. So those are whatever the image has. Thank you. So now we have talked about the numerical data. We have talked about the image data. What about the textual data? How do computers understand text? Or how do we make them understand text?
Well, from the compiler world, I remember lexical and semantic, we have all those complicated graphs and stuff like that to form structures.
You're thinking too hard.
It's a grammar, right? Language has a grammar, right? So if it is given the grammar for that language, that should be.
Yeah, that's rule-based, right?
Yes.
Which is not what this is, right?
I'm sorry?
This is not rule-based. This
This is not rule based, yes.
Right, that's the big difference, right, between
Yes.
So you
learning this way and rule-based programming.
Yes.
Set the software up so that it learns
Yes.
and figures it out rather
Yes.
than you figure it out.
That is right. But in order to even get to the point where we let the machine learn, it has to understand. But for it,
Character recognition
character recognition,
with a good dictionary to back it up.
yes. So I think you all have bits and pieces of it. So let's take a full picture. I'll just give you a simple answer. We actually have to convert the word into numbers. So
Okay.
it's simple. Simple answer. So you were thinking too hard.
That's data augmentation, is that?
Data augmentation is when it's slightly different. So data augmentation is when we have data, but data is not enough. So we create new data. So let's say we have an image of a cat, but I want to create varieties. I want to do shifts or things like that. So you're augmenting the data. So that's slightly different.
We're adding value to that data, basically.
Yeah, to me, it would be the parsing, whatever you could between punctuation, space, what
Yes,
have you.
yes.
Recognizing it, and
Yes.
as we were talking about tokenizing.
Yes, you got tokenizing. That's the word. That's actually
That's fundamental concepts of lexical analysis.
exactly. So let's look at so before we even do any machine learning or deep learning on text data, there is pre-processing involved.
Oh, wow.
You don't have to read through it, but just wanted to highlight. So let's say we have a raw input right here. At the end, machine learning can only understand numbers. So how do we go from here to here? It's basically, in English language at least, we know we can break the words into by the space, and each word we call token. So we tokenize it. Right here, something here. So before we tokenize, we actually have to clean the data. For example, so let's say in the English language, we can write the as a capital T, or we can write the as a lowercase t, depending upon where it is in the sentence, right? Now, when we are teaching the machine learning model, the with the uppercase, the with the lowercase t, are there two different words or is it the same word? Do we use the same token for both, or do we use different tokens? So these are all different questions we have to solve before we even touch the machine learning model. And then talking about punctuations, are the full stops important for the machine to learn? If there is URLs, so there's a lot of cleaning required before we feed the data. So this is just a basic pipeline, and this is not standard. This is this can vary depending upon the problem we are trying to solve, right? So the idea is we take this sentences and then we remove the things that we are not necessary and we divide that into words. Usually we remove the, usually be lowercase, but not always the case. And then we have something called stop words, lemmatization. That just stop words just means the things like the things that are there as an article but don't actually have a context, so we call them stop words. So if we can remove them if we want to. And lemmatization is, so we have, let's say, driving versus drive. So the root word is drive. So if we have driving, we convert that into a root word. So that's called lemmatization. Okay, so then we do all that, and then we build a vocabulary, and then at the end we can represent those words by numbers. We use dictionary. We build a dictionary for that, right? Okay, so once we have that, and then I can feed this data, this numerical data, to a deep learning model. And then we do the same thing. We learn from the data. Okay, so we took a segue. So far we learned about the deep learning model perceptron. We learned about multilayer perceptron. We learned about the convolution neural network. And I wanted to show this slide because what we have not discussed is the neural network that are used to process textual data. So that's what we will be learning next. Here, we have a deep learning model called recurrent neural networks, and there are several kinds, such as LSTM, GRU. We won't go into the details of these, but why they are necessary? Why can't we use the multilayer perceptron or even the convolution neural? Why can't we use those?
I thought these had memory or something.
Yes, absolutely.
Yeah.
Yes. So we needed these set of neural networks because we wanted to have the memory. Because when we have a sentence, we want to have the context. If we want to know what existed, what words existed before. So we wanted that memory. So that we can't get with multilayer perceptron or CNN. So that's why we needed to build new models, and we call them recurrent neural networks. These are still used today in papers, research papers that we read, but mostly these have been overtaken by a more powerful model, which most of you probably know. It's called transformer. State-of-the-art model today is transformer. It was introduced in 2017 by a team at Google to solve natural language processing problems. But since then, it has been used for even the image, even on the image data. It's shown to perform even better than the convolution neural networks. So this is, I would say, the state-of-the-art model when it comes to deep learning. So let's look at this. This is an architecture of a transformer model. And what it has is, if you break this down, what it has is, it has two things in it. It has an encoder and it has a decoder. So it is a encoder-decoder architecture. And the stuff inside the encoder and the stuff inside the decoder, it's pretty much the same. As we can see, we have something called multi-head attention, we have something called add and norm, feed forward, big words, but don't read through it, you know.
We'll treat it like a black box.
Yeah, treat it like a black box for now. If you want to discuss more, that's for another lecture, and I would be happy to discuss the details and stuff in a later talk. So it's an encoder-decoder architecture, and the problems that it has solved for us is things like translation, text summarization, text generation, and many more. So let's take an example. Let's say I want to do a translation from English to French. So how it works is, obviously we'll have to do all of the data pre-processing that we did to convert that English text into numbers. once we have done all of that, then we feed that into encoder. And this encoder encodes that English data, or actually the number representation of the English data. It encodes that into what we call embeddings. So what we get here is what we call embeddings. And those embeddings are then fed into the decoder, and the decoder is supposed to decode those embeddings, and it is supposed to give us the translation in the language which we said was French. So English goes in, French comes out. And we have to train it, and it's trained again using lots of examples for a lot of iterations. And we as a machine learning practitioner, we decide what kind of metrics we want to use to evaluate this model before we even put it out there. So the key features of a transformer the key features are that it is able to do non-sequential processing. So it can process the entire sentence at once. Whereas the RNNs that we saw in the previous slide, you can only feed them word by word. So it is sequential. This, because you can process a whole sentence at once, it is non-sequential. So that means we can use multiple GPUs at the same time to process our data. So that's the biggest benefit. And then other things that were critical here was something called attention, or self-attention, or cross-attention. Attention is just like you probably have guessed. The attention is like, if we think of how we look at things, we know where to focus, right? So if you're reading a sentence, we know which words are important in a sentence that make it meaningful sentence. If you're looking at an image, we know, example, when you're driving. So we are not like going through each pixel when we're driving, right? We know which is an area that needs attention. So that's exactly the idea here behind attention. So it learns during training where it needs to attend, which parts of the word, which part of the sentence which words in the sentence are informational and should be linked together. It learns all of that. That's called attention. Okay, so this is the paper that the title of the paper is called Attention is All You Need. This is the paper that introduced the transformer model architecture. Yeah, this was in 2017. So if you are a machine learning practitioner and want to build models, I would say this is the paper that we should read. Very critical, because a lot of the models, a lot of the things that exist today are built on top of transformer architecture.
Cool.
Okay, let's take a pause. Are you excited about using AI, or are you confused?
No, actually, a little bit more enlightened, at least you won't feel at a loss when they throw all these terms
Yes,
around.
exactly. That was the whole intent, to just be aware what the terms are, not necessarily understand every piece of it, because that's just not possible for anyone if you're learning. This,
Now I have to ask, what's this here?
what is this?
That's how we feel.
And this is how you feel with which one? I had different
Well,
expressions.
we started over there with a question mark, and then we're over here.
So we went
Oh,
from
okay,
right
got
to
you,
left
got you,
here.
got you, got you. Yes. By the way, this image was created by AI.
Well, obvious.
Yes. All of you as a person to use it, we just have to give it something we call prompt. You say, hey, I want to, in this case, let's say I want to
Sure.
see a Pikachu, which what this character is in amusement, in confusion, something like that, right? So it comes up with this.
Cool.
Yeah. Okay, so that was all the math and all the detail, all the terminology behind where things are today with machine learning or deep learning in general. Now, let's get into real discussion. How do we use deep learning today? Because if you don't want to learn of anything that we said, that you can still use machine learning. I mean, when I say machine learning, I just use it very vaguely. I just mean anything that's AI related. So how can we use AI on our daily lives?
Googling.
Google. Yes, Google is actually, that's a good example, and I'll talk about it in this slide here. Yes, that's one way. So there are many different ways to use AI in our daily lives if we want to. And actually, it's inescapable because, like you said, AI is
We're drowning in it.
Yes, we are drowning in it.
So your chart actually would suggest why when someone had me use Bard,
Yeah.
it wasn't giving me as nice of answers as the other one. The ChatGPT has a huger base,
Yes, that's true. Yep.
huge.
Yes, it does matter. It does matter, like how much data we use.
So, question, why does Llama 2 have 3 different sizes?
Yes, there's just 3 different types of models. You
All 3 models,
different
okay.
different varieties to use.
Okay.
From, yeah.
And there are probably going to be many more because,
Yes.
I've heard other countries are like China is going to build a competitive to all of these.
Absolutely.
They're going to come up with even more.
Absolutely. Yeah. It's a race we are in right now.
I don't think there are enough computers in the world for more and more of these.
And I would say it's a bit of a limitation. Yes, that's a limitation because as a researcher, let's say you have all the knowledge, but how would you get the compute to train this amount of data? That's where the money is, right? So that's why all these big models are out there that are working really fine. They're by Google, it's Bard, OpenAI, Meta, Microsoft, because they have the money. They have all the resources.
I think I heard that ChatGPT has learned like billions of documents,
Yes.
just billions.
Yes. Yes. So
See, we're now getting into Carl Sagan territory where you can't even use the word billions and billions. It would sound puny to this guy. He needs more than that.
yeah, absolutely. So that's the thing about deep learning models. They do need a huge amount of data to perform well, to generalize well. So that's why ChatGPT performs better because it has been trained on.
My simple question is, suppose I ask ChatGPT, write an essay on some research topic. What does it do? How does it get the result of 10 pages?
Yes. We don't know the details. They have not released like how it comes up with the answer, but we do know like the general framework. So it has been trained on entire internet, like all the textbooks and everything. So it has the knowledge base and it has learned the pattern. So based on that pattern that it's learned, that's how it's able to like generate the next word when it's trying to generate the whole text for us.
Going along with what you're saying, I was kind of following with Google when they open sourced their AI module, people panicked.
Mm-hmm.
Well, they knew they had the repository of training data.
Yes,
Without the training data, you can have the source code,
Yes.
but it won't do much.
exactly.
And
Absolutely.
And then, going to your thing about the other one, the more papers that they have put into there, and the more people have interacted with it, the more its data is tuned to produce a product.
The other thing I'll say is it's only as good as the data it's been trained on.
Yes.
Many years ago at some storage conference, they were talking about AI. I said, that's first of all the wrong term. What you should really call it, it's data-driven fancy algorithms. If you give it nonsense data, it'll give you nonsense answers, and that hasn't changed.
Yes.
Now, the more better data we give it, then it'll start appearing more and more useful. But without the data, it's nothing.
100%.
With Professor Subra's class, he's about architecture, so when they were looking about the computers and the things that they would use for AI, and that's where I learned that they make a special processor as opposed to using what was out there. They started with what was out there, and then other people more or less specialize. And as we pointed out, a lot of the times we go to the GPUs or the NVIDIA, which was another interesting group of classes that, thanks to things here at the school, they drug me into and introduced me to. And I just throwing it out there, they use a different type of thing for processing these
Interesting.
things.
I have to
Yes.
look into that, cause GPU, sorry, go ahead.
Yeah, it'd be interesting to talk about exactly what GPUs do and how they solve, what the problem is that they actually solve.
Okay, we have an answer for that. I just recently contacted NVIDIA. I know tons of people out there. They've agreed to come, at sometime in September at a venue like this and talk about what's going on, the latest in their GPU stuff and where they're focusing their efforts.
I've heard of these concepts called fuse, multiply, add, where they have these, you can take two 4x4 matrices, you start F32, they use mixed precision, where they come down to F16, multiply them together, then convert them back to F32, and then sum into the third matrix. And supposedly they can do like thousands of these in a single
Yeah.
clock
That's
cycle.
called high performance computing.
Okay,
And that's the compute intense
But
sheet.
CPUs don't do that, GPUs do that.
No, CPUs do it just as well.
Oh, really?
Remember a guy called Seymour Cray?
Yes.
He started all that.
When you
Oh,
make,
well,
when
they're
you
talking
make
about
just as well
compartmenting
though,
your
it's
data.
not as,
That's what's absolutely necessary to be able to put it into a GPU, because you can't do calculations that are dependent on a previous thing. And moving stuff in and out of the realm of the GPU to the other part, that's a huge penalty. But I just want to share with you when we talk about compartmentalization, that was very big key to the large scale processors that we were studying in DSP class and the GPUs, because they function that way. They can't have it dependent on a previous part, or they can no longer do the efficient process.
GPUs are nothing more than assistive computing. And their genesis came from the graphics world because they would do tons of calculations and
Transformation.
and all those, it was really mathematical operations at scale. And so inside the GPUs, like thousands of cores, but specialized for those fuse, multiply, and all those kind of things, which all came from, the vector world and the supercomputing world and graphics world, repurposed for this. But behind it is still matrices.
Yes, but it would be good to, like you said, have somebody,
Yeah, we're having the NVIDIA folks come and,
because I
lots of other
honestly
people are
don't
there.
know, just like some of here, I don't know what's actually happening inside. I use them to train, but I have no knowledge.
all
What's
IEEE.
happening?
I have one
You
more
mention
simple
IEEE,
question.
they come running and say, we're happy to tell you all about it.
Another
So
simple
Brad,
question. Suppose we ask AI to design an engine controller. It may do something.
Yeah.
Is it going to affect all the engine control people at GM? Can they reduce the number of employees to half?
I think that's a good question, and it's yes and no.
Well, let's ask all the Hollywood writers and
Yes.
actors about that.
Yeah.
They're more worried about
Yeah.
it than present day engineers, but I think the way things are going, the more training and more data you give them, it's possible they'll
Yes.
start doing simple, elementary, rudimentary, but who knows what's going to happen 10, 20 years from now.
Yeah, I mean, as of today, if it gives us the answer, we can't take human out of the loop. We do need to do fact checking as of today. But that could obviously change as the models learn more and more and becomes better and better.
And we also have to have laws and regulations also
Yes.
about it. We can't just say, all right, everyone spend your money and get rid of the employees and make AI do all the work. I would ask those nincompoop CEOs,
Yeah,
excellent, you want to throw everyone out of work so the products you design will AI, who will buy them? If they don't have work, they won't have money to buy products. Have you thought of that? maybe your AI isn't that smart after all.
So it goes back down to the HR or the other sales pitches. Cause I go back, way back when we had, the ERP systems for telling people how to run their businesses. And they convinced them to let go a lot of their staff because this thing would take care of it. And then they didn't like the decisions that was being rolled out by them. So this is why you need to have people, humans, interact and pay attention to the data. So
it's not going to be instant, I would say, for some things maybe instant, but for most things it's not like instant use of AI and then humans. It would take at least a generation to still have human in the loop, but then maybe then the AI is ready. But then by the time we should teach better skills to the kids that are still in school so that
Subra, don't worry, you'll be retired by then.
My worry is we can replace all the 100-level teachers by AI teachers, AI robot.
that's a real concern.
Yeah. Concern is real, absolutely.
But I was gonna say, because there are some jobs they're gonna die, but at the same time it's creating new jobs,
Yes.
new job.
Yes.
So it is kind of balance each other.
We'll need humans to feed it more text, maintain those computers,
Yeah.
and once in a while pull the electrical plug too.
Yeah.
Say, oops.
Yeah. So let's just few more slides and we'll.
Yeah, let's wrap up.
for the slide.
Yeah.
So we have these BARD, ChatGPT, Llama 2. They generate text for us. They belong to a family called large language models. But here, for them to be useful, we have to have a human, a creative human, who is giving them leading text, which we call prompts, to come up with something. Okay, here is the answer to your question. If we ask them to create something for us, they will, but it's not 100%, it's not deterministic. So sometimes what they give us just a bunch of text with a bunch of nonsense. And in machine learning world, we call it hallucination. Sometimes these models hallucinate.
No, it's good. Even machines take drugs.
Yes. So that's a real term. Here, just to show an example, probably everybody has interfaced with ChatGPT here. So you ask a question and give text out. Here I just asked a simple question. I said, hey, prepare a budget-conscious itinerary for my trip to India. And it gave me this. It has actually all 10 days. It was pretty good. So it's a good starting point for some. I'm from India, but if let's say somebody is not from that country, it's a good starting point for them to start with this itinerary.
One thing is missing.
Yes.
They have to tell you, watch out for pickpockets.
It is there. It was there.
It was there?
Yes.
Then somewhere in the internet, somebody posted all
Exactly.
those experiences and it took
Yes, it
that
would say,
into account.
do negotiate, don't hesitate to negotiate with the vendors, because
Oh,
we do
good,
that in
good.
India. We had it all done.
I did use the ChatGPT to plan my trip.
Nice.
So I wanted to see Bombay. So I said, I have 2 days in Bombay, what can I do?
Yeah.
Then it gave me a list.
Do you like it?
It was a
Yeah.
very good suggestion.
Yeah. So it's good enough, but
So the lesson in this is use AI to be your assistant.
Yes.
Don't let AI dominate you.
yes,
And that's what everyone, every government,
yes,
every society in the world should determine
absolutely.
and not become greedy or
Yes,
bend ethics rules.
yes.
Because if we let them do that, then we're doomed.
Yes.
There is AI ethics war going on.
Yeah, it's pretty poor state of AI ethics, I'll tell you that.
Yeah.
Yeah, so just an example here. Like you said, we want to use AI as an assistant. We should use AI as an assistant to augment whatever we're already doing. Because if we don't do that, maybe we will be left a little bit behind than other people who are using it. And we have a lot of tools available as we speak. There are tools to generate images. I know somebody who is writing a book and she's using AI to create images for her book. And AI can generate text, which we already saw in the models that we saw before. And then AI can also generate music. So use these tools, adopt these tools. And a lot of them are easy to use, like ChatGPT, you just have to put a prompt. So what kind of education do we need for, let's say, the upcoming generation, people who are still in the middle school, high school, for them to be ready when they're out there for the jobs and stuff? So what kind of skills do we need?
Making safe and helpful robots. Making safe and helpful robots.
What kind of skills should we teach them in the schools?
I would think it's simple logic design, ethics, those two should be the main.
Absolutely.
The number one thing we should teach everyone is critical thinking
Yes,
skills.
yes.
That's the most important.
Yes.
Yeah, because if
Yes.
they became lazy and kept going to ChatGPT
Yes.
for everything,
Yeah.
then you lost that creativity.
Yes.
And that's the key thing is
Very
to
important.
show them how to use a tool, but how to be independent of it.
Yeah, so critical thinking, creativity. Really, those are the things. I personally feel the same way. So we still need to teach this creativity, problem solving, lifelong learning
Very
because
important.
because as we are here, AI wasn't there. Like it was, but it was not as prevalent as it is today. Maybe 10 years ago, but we are learning. Everybody in this room is learning, right? As we speak, so it's a lifelong learning and being flexible to move with the technology, use it as an assistant, like you said. Yeah, so I still believe that education is important
Very important.
because that's where we learn how to solve problems, even though they're toy problems, but it's important. Okay, so this is something that came up, something I saw on the internet. So this is a book called Impromptu, and when this book first came out, there were headlines that said AI wrote a book,
Oh,
and it became the bestseller. That was the book. Sorry, that was that's what the news said.
the headline.
Headlines. And next thing you know, all the writers are scared because they're like, oh, now our jobs are gone. But if we actually read the book, I glanced through it briefly. It's not written by AI. It's not written, like here, it says by Reid Hoffman, he's the author, human, and he says with the ChatGPT 4. And if we read this book, it's actually written by Reid Hoffman. All he has is, he just asked questions to GPT-4 in this case, and he shared those responses here. As you can see here. So here he asks, what impact will AI have on creative people, such as musicians and other artists? And then GPT-4 replied, it's both positive and negative. And then it says, what are the positive impacts? It says, what are the negative impacts? So there is nothing creative about this. This is a generic response that we as humans know, right? So don't be scared. Do read the content yourself and then make a judgment. But here, again, don't read into the words here. This is something I got from LinkedIn. I don't know who created it. It says generative AI, so I just put that here. But these are just a different
Actually,
tools.
this will make a really good game. If you hate AI,
Yeah.
I read the board and throw darts at me.
Yes. Then go learn that tool.
Yeah, that's
Yes.
cool.
Yeah. Yeah, so there are tools for productivity, music, whatnot.
Are these tools combined expensive enough that we basically need a universal basic income just to pay to use them?
Right now they're affordable. Like right now they are like $10 a month or something. Some are free. So, but I would imagine like as there are
Maybe
more
like cable
companies.
channels and streaming services, you're paying 10 a month one day, the next thing you were selling your house.
I know, I know where you're going, but yes, those are the concerns, right? We want to enhance our results using AI tools, but we don't want to go bankrupt using all of them.
We have to wrap up soon.
Okay, so just one last slide, two more slides on this. This we already know, so the human is still in the driver's seat. We're using the AI because it has knowledge, it's trained on a lot of things, and we get enhanced results. So now we come to your question. So AI can solve a lot of problems, and it is solving a lot of them, but I feel that we should be more strategic in identifying what problems do we really want the AI to solve. And I feel we should prioritize the problems that we as humans it's difficult because high dimensional problems, and also maybe some places it's dangerous to go, like in the, to put out the wildfire, right? I feel we should strategize and
Climate change, that would be number one on my list.
climate change as well, yes. Absolutely.
Actually, I would put number one, beat some sense into politicians, that might be more appropriate.
Right now, they don't know what AI is,
Oh.
so we have the upper hand.
Actually, I think politicians,
Their assistants.
as far as their intelligence is concerned, that's quite artificial, yes.
Yeah, that's true. Yeah, so I just slide here, and these are the problems that I'm working in and I'm interested in. We can talk more if you share the interest, so I'm skipping that for now. And basic problem that everybody is impacted by. So why can't we just solve this problem? And it is solvable by AI.
Oh, that famous graph.
Gartner curve. So where is this technology going? So this is a Gartner curve, that comes out pretty much up here. So for 2022, this is the Gartner curve. It's actually quite interesting. Take your time, go through it when you go home. It's basically telling you this is the time, and it tells you when a new technology comes, that's an innovation trigger. And then there's peak of expectations for that technology. And then there is a disillusionment. And then there is again enlightenment. And then we have that mature technology. So AI or generative AI is here right now. So we have a lot of
A hype
excitement.
curve.
Yeah, it's right here. And the self-driving cars are right here. On the
It's
So
a little far away.
yeah, so it was here 5 years ago. I remember.
Yes, that's right, yeah.
Yeah. So, but we realized it's a difficult problem. So right now we are in the disillusionment. Yes.
It's got physics informed AI on the bottom left, right next to AGI, which is the more than 10 years triangle.
Yeah.
What exactly is physics informed AI? And what is the difference between the two? Physics
I mean, I
informed
know what is artificial general intelligence. I don't know what it is.
I can. So it's physics informed means you basically bring the physical model, and so you bias it with that.
Yeah, yeah.
Oh.
It's simple word that's
So basically coupling with real world data.
physics.
And the other part, artificial general intelligence, is just general intelligence, like human level. Right now, what intelligence we have is called narrow intelligence because we're solving specific problems.
So PIN is big in manufacturing.
No.
Physics informed.
Oh, yeah. And risks.
Yeah.
Oh, about 6 months ago, that movie,
Yes.
Coded Bias,
Yes.
we showed it in the IEEE meeting like
Cool.
this year.
Cool. Yeah, so that's
Yeah,
the
we
movie.
did, yeah.
I'm sorry, that's the movie here. The documentary. If you want to
Yeah,
watch.
yeah.
Very good documentary.
You can also see it on Netflix
Yeah.
too, yeah.
Oh.
But we actually had an, I think it was in February of this year we did it. I can't remember when. But we
My
showed it
fear
at
is
IEEE meeting.
in 1960s, there was too much expectation out of AI.
Mm-hmm.
We all thought AI is going to rule
Mm-hmm.
at during 1960s, 70s.
Mm-hmm.
Then it had a
Yes.
depth.
Yes.
All the AI professors changed their career to something else.
Yes.
Then it was not even taught in the university.
Yes.
Now it has come back
That's right.
with more speed,
Yes.
and then it is creating more
The
fear
main
among
reason
us.
is because computers got more powerful.
That's true.
Yes. But I don't know whether this also will pass, because like when robotics came, everyone thought, oh, it's going to replace all the laborers.
Yes.
But then it is still continuing.
Yeah. So what we saw was a prediction. It could change. So it depends if they're putting too much expectation, but maybe we get there, maybe we don't. So it could change. But you're right. We did have AI winter back in 70s, 80s, but it came back now.
Yes.
Okay, so here I'm skipping because of the time, but I also want to end with the strategies. These are each of these are research areas, by the way, and then the regulations. And if you're interested,
That was new, yeah.
I'm sorry,
They just updated that.
this
The
EU.
EU Act.
Yes, yes, it is. Yeah, it's fairly new. Like, but we don't have anything in the US, but this is just the beginning.
No.
But that's the end of the talk. What I really want to encourage is, because the goal is we want to make AI that is unbiased and is available to everybody who wants it. So each one of us plays a real role to, if you know how to use it, share the knowledge. But then also when you're building the models, we need to have the diversity of the data, because that's how they will be less biased. And also inclusivity. What I mean by that is, right now, all of these natural language models, they mainly operate on English language. We have a whole set of languages in the rest of the world. We need to broaden, rather than just one, we need to broaden the application so that the entire group is covered. So that's the.
The plus side is, I assure you, China is not using